Okay, so let's go ahead and bring up the blueprint for enterprise infrastructure. Okay, it says Enterprise Infrastructure version 1 is an 8-hour hands-on exam that requires a candidate to plan, design, deploy, operate, and optimize dual-stack solutions for complex enterprise networks. So first and foremost, this means that any of the topics that they're referring to, it's going to be both for IP version 4 and for IP version 6, even if they're not explicitly saying that in the blueprint. So for example, for EIGRP, we're assuming that we need to do dual stack routing, even though it doesn't say anything about EIGRP v6 explicitly in the blueprint. Candidates are expected to program and automate the network within their exam as per the exam topics below. So this is going to be related to the SD-WAN, the SD-Access, and then the automation system or automation section, which is a new addition to the blueprint. The following topics are a general guideline for content likely to be included on the exam. Okay, so they always like to give themselves that out there saying that, hey, if we didn't list it explicitly and you got tested on it, you can't sue us or you can't complain. Your knowledge, skills, and abilities on these topics will be tested throughout the entire network life cycle unless explicitly specified otherwise within this document. The exam is closed book and no outside reference materials are allowed. What they should say here, though, is that the Cisco documentation is accessible during the exam. So as we go through the different technologies, we're going to be spending a lot of time in the documentation, looking at where can we find those particular technologies, and then for miscellaneous topics, how can we use that to build config examples that we can pretty much copy and paste from the doc CD into the command line in order to solve different questions. Okay, our first section in network infrastructure starts with layer 2 switching in Switch Campus. And this is pretty much a one-to-one carryover from the RNS blueprint. We are going to be starting with this as our first technical session for today. Hopefully this is going to be review for most people, just regular Ethernet bridging. There's not a ton of advanced topics we need to talk about. Maybe some minor things like VTP version 3, troubleshooting Ethernet port channels, troubleshooting rapid spanning tree protocol maybe. But in general, this is the CCNA, CCNP level, just how do we get access to layer 2 switches, how do we configure them so that we can forward traffic between the layer 3 routers. Okay, so we have under spanning tree per VLAN spanning tree plus, rapid spanning tree per VLAN plus, and multiple spanning between a pair of protocols. How is the administrative distance going to come into play when we choose one path over another? VRF Lite, we're going to see this in multiple cases. We're going to see this as a standalone feature where we have multiple routing tables, and then we're going to see this also with MPLS layer 3 VPNs. So we may hold off on this for now and then come back to this when we get to the MPLS section, because it's going to make a little bit more sense why you would have multiple routing tables when we're dealing with an MPLS type design. Don't exclude static routing as part of your preparation, because there are some minor caveats we need to talk about with this, like reliable static routing. How can we tie a static route to an IP service level agreement to give it a little bit more intelligence? And don't assume that in the actual CCI lab exam that you cannot use static routes. So generally, there's going to be some usage guidelines in the beginning of the exam that say, do this, don't do this. And a lot of times one of those line items is don't use static routes, but it's not guaranteed that that requirement is going to be in there. So you don't want to use some off-the-wall solution that you have to go way roundabout out of the way if something with static routing is going to just solve your problem. Okay, VRF aware routing with any protocol. So this is going to be grouped in with MPLS. Route filtering with any routing protocol. We're going to go through those individually as we go through EIGRP, OSPF, and BGP are going to be our big 3 routing protocols. Same as with manual summarization with any routing protocol, redistribution between any pair of routing protocols. And also for this section here, when I had done the last run of this class for routing and switching version 5, route redistribution was pretty complicated because we were dealing with RIP version 2, eIGRP, and OSPF. But now that RIP version 2 is removed from the blueprint, the redistribution section, we will cover it, but it's definitely not going to be as detailed or as problematic, I should say, as we saw in previous iterations of the exam. So redistribution is going to be kind of a corner case that we need to deal with in MPLS as we're redistributing updates from the PE to CE routing protocol to BGP. But beyond that, we don't really need to spend a ton of focus on redistribution. Routing protocol authentication, we're going to go through these individually as we go through eIGRP, OSPF, and BGP. And then last but not least, bidirectional forwarding detection. This is going to be a way that we can quickly figure out, is there a layer 2 circuit failure, and tell our upper layer protocols that they need to reconverge without having to wait for the hello and the dead time to expire for the upper layers. Okay, next, section 1.3 in eIGRP. eIGRP adjacency, so we'll talk about just what are the basic requirements of forming eIGRP adjacency, what are some of the problems that we could run into. So we'll look at the configuration, the verification, but also the troubleshooting of these protocols, because there is a distinct troubleshooting section in the exam that you're going to be faced with when you get to the actual lab exam. Okay, we'll also talk about the general operation. So how do we review the topology table, look for any problems that might appear in the eIGRP topology, like what happens if you see a prefix that has an infinite feasible distance. We'll look at the different packet types like the query packet. Okay, as we're talking about the queries in stuck and active, and this is going to relate to our DMVPN topologies and when we look at the eIGRP stub feature. Okay, eIGRP load balancing, we have equal cost and we have unequal cost load balancing, and we have additional paths. This is going to be another line item that is going to go under DMVPN. So in DMVPN, if we have two spokes that are attached to the same LAN segment, they're both advertising this up to the hub. The hub is normally going to only advertise one path for that remote network. So with eIGRP additional paths, similar to BGP add path, we can have basically the route reflector advertise multiple paths, and then we could have path diversity as we're going across the DMVPN. Okay, eIGRP named mode is going to go along with the wide metrics. So from a configuration point of view, there's not going to be a ton that we need to deal with when we're changing from the classic metrics and the classic autonomous system version of eIGRP to the named mode. But this is something that we need to take into account. There is some change in the behavior as we're going from the autonomous system mode to the named mode. Okay, then lastly, we have optimization, convergence, and scalability. Fast convergence requirements. So this is going to be our feasible successors and how we can basically design the network so that we can run IP fast reroute on a single hop basis. For eIGRP, this basically means that we have a backup path. So we have our primary path that is the lowest cost. We have an alternate path that the upstream neighbor has a lower cost than us to reach the final destination. We consider them to be a feasible successor or a backup route. The idea then is that we can install both of those routes into hardware, and if there's a problem with the first successor, the primary route, we can just immediately switch over to the secondary feasible successor without having to do a routing protocol recalculation. Okay, then leak map with summary routes. We'll talk about this within the scope of DMVPN. Why would you want to leak specific prefixes when you're doing a summarization? Mainly this is going to be for the purpose of traffic engineering, that we want to prefer one path over another. And the same is going to be true with the eIGRP stub feature with its leak map. Okay, next we have OSPF, and notice that they're denoting both OSPF version 2 and OSPF version 3, where OSPF version 2 is going to be for IPv4, OSPF version 3 is going to be for both IPv4 and IPv6, where originally it was designed just for IPv6, but now it has extensions to run IPv4 routing. So essentially everything that we talk about in OSPF v2 will rehash that in OSPF v3, and we'll see that they're very similar in the operations in terms of how do we form the adjacencies, what are the requirements of the network types, how do we do the path selection, and so on and so forth. So if you understand OSPF version 2, then you inherently are going to understand OSPF version 3 once we get past the hurdle of the IPv6 addressing format. Okay, so OSPF adjacencies, we'll talk about what are the requirements to form adjacency, what are the attributes that need to be unique, what are the attributes that need to be the same between the devices, and we'll spend a bunch of time going through troubleshooting what happens when two OSPF neighbors don't come up. There's a number of different options that are in the RFC that say they either have to match or they have to mismatch. For example, we need unique IP addresses in order to form adjacency. But in the troubleshooting section, under the time crunch, we need to make sure that we have some sort of structured, logical approach that we can follow so we know how we can troubleshoot the adjacencies. Okay, network types and area types. So network types, these are referring to like broadcast or non-broadcast. This is going to be an issue when we get to the dynamic multi-point VPN, and we're running OSPF over a partially meshed network. So we'll talk about how the different network types affect the operation over DMVPN. The area types are going to be talking about stub areas, not so stubby areas, totally stubby areas, etc. And this is going to affect traffic engineering of how we select the exit point out of the network and how we can modify which direction the traffic flow is going on effectively a per prefix basis, which is very difficult to do in OSPF to begin with. Okay, operations, general operations, doesn't really tell us much there. Graceful shutdown, generic TTL security mechanism. This is the one that comes from BGP, which is BGP TTL security. So this is another way to make sure that someone is not trying to take over the OSPF network and insert false information. So we can just say that when I'm learning an OSPF update, check the time to live and make sure the time to live is coming from one hop away, which is going to be my OSPF neighbor. So this is going to prevent against packet injection attacks that are coming from further away in the network. Okay, 1.4e, optimization, convergence, and scalability. So metrics, this is going to be just how we can change the metrics in order to change path selection. We'll talk about some of the tuning of the SPF algorithm. So how do we throttle the LSAs, SPF tuning, fast hellos, and this is also going to go along with bidirectional forwarding detection, which was listed in the protocol independent section. Okay, LSA propagation control with area types. What this means is the stub areas, the totally stubby areas, the NSSAs, we're going to limit what type of LSAs that we can accept into the area by defining a different type of stub area. This is different than the OSPF stub router feature. So we'll come back to this as we get into more details with OSPF, but these definitely do get confused that we have the stub router and we have the stub areas. Stub router is going to be to recalculate around that device when we're basically trying to take it out of service. Okay, loop-free alternates. This is going to be IP fast reroute, where we run an OSPF shortest path first from our perspective. We then run it from other routers' perspective within the area, compute a loop-free alternate, and then we can have an active and backup path for OSPF. Kind of similar to EIGRP, how it deals with the feasible successors. Then last but not least, we have prefix suppression. This we're going to look at within the scope of MPLS and how this can optimize the number of routes that we need to have in the routing table and optimize the number of labels that we need to have in the MPLS label information base. Okay, next 1.5 we have BGP. So iBGP and eBGP peering relationships. So how do we start the sessions to begin with? So just regular peerings. We could have peer groups. We could have update groups. We could have peer templates. So we'll talk about the differences between the peer groups and the templates. When would you want to use one versus the other? A common use case of this is going to be on a route reflector. So if you want all of your route reflector clients to behave the same, we could create a template that says all of the devices are in remote AS1. We're sending the update source from our loopback. Under this address family, they're going to be a route reflector client, and so on and so forth. So it's basically going to be a way that we can save on syntax, and the BGP process can save on processing in the background, that we take one update and send it to the template or to the update group, as opposed to doing one update per route reflector client or per remote peer. Okay, active and passive peers, timers, dynamic neighbors, 4-byte AS, private AS. These are all just referring to the basic BGP starting the sessions before we start to talk about the network layer reachability information and doing any of the advertisements of the actual routes. So we'll spend time going through how do we just set up the BGP peerings and talk about what are some of the trouble issues that we could run into. For example, BGP dynamic neighbors, will look at this within the scope of DMVPN. So on the DMVPN hub, we could set up dynamic neighbors where we're listening for the spokes to start the session, which means that when we add new spokes onto the DMVPN, we don't necessarily need to update the configuration of the hub. Okay, next we have BGP path selection. So what are the attributes? We'll take a look at this in the documentation, the BGP best path selection algorithm. Talk about what are the attributes that we would mainly be using for modification of the path. Weight, local preference, MED, AS path information. We'll talk about what direction you would set those in order to affect the traffic flows. Where weight and local preference, we're generally setting these attributes inbound. They're going to affect our traffic outbound. Where MED and AS path prepending, we're going to set those attributes outbound, and those are going to affect our path selection as the traffic comes back inbound. Okay, next we have routing policies. So attribute manipulation, conditional advertisement, outbound route filtering, standard and extended communities, and multi-homing. This is going to be going along with path selection, but they're basically saying, okay, now you know what path selection is. Now we want to implement the actual routing policy. So attribute manipulation, this would be like doing an AS path prepend to say I have two paths to the WAN. I'm going to prepend out path B. The idea is that I want to receive traffic in path A as my primary and then fail over to B if MPLS, and some of them are going to be related just to problems we have when we have overlapping BGP autonomous systems. Convergence and scalability, route reflectors, and aggregation AS set. So hopefully, as everybody knows, iBGP by default uses a full mesh of peerings in order to exchange the information between the peers. If we don't want to do a full mesh, we could either do route reflection or confederation in order to cut down on the number of peerings. That's what it's talking about here in convergence scalability, that we don't want to have to add 999 peers if we add our 1,000th router to the BGP topology. Okay, other BGP features, multipath and add path. This is going to go along with MPLS as well. So how do we load balance within the MPLS core? And when we advertise routes to the route reflector, the issue is the reflector is only going to choose one of those paths and advertise it on. So BGP add path is going to be similar to EIGRP add path that is going to allow us to advertise multiple prefixes from the route reflector onto the edge. Okay, next we have multicast. where in the version 5 blueprint, problems with the reverse path forwarding check failing, and how can we work around that, like with a static multi-guess route or with a multi-guess BGP configuration. Okay, next under PIM, we have PIM in sparse mode. Okay, so no dense mode anymore. We only have to worry about sparse mode. With sparse mode, we need a rendezvous point, so we'll talk about the different ways we can do that, either statically with Bootstrap Router or with AutoRP. When we define the rendezvous point, what groups is it going to be servicing? So is it going to be servicing all groups 224.0.0.0/4, or are we splitting the load between multiple rendezvous points where they're servicing different groups? Okay, bidirectional PIM and source-specific multicast, these are going to be essentially the opposites of each other, where bidirectional PIM only uses shared trees that are going through the bidirectional rendezvous point, and source-specific multicast only uses shortest path trees that are coming from the sender directly to the receiver. So we'll talk about both of those, and we'll talk about redundancy. Bidirectional PIM, we'll talk about a feature called Phantom RP. Source-specific multicast doesn't need the rendezvous point. And then in regular sparse mode, we'll talk about Anycast RP, which is going to be our redundancy for either static RP, BSR, or for AutoRP.